Good morning, pre-calculus. We are here just for a brief period of time this morning to do a quick, what I call a dress rehearsal for the review of the entire semester. So what all do you need to know coming into the final exam that's going to make the difference? This review is going to be posted online later on this evening in a more polished format, so this is just kind of a dress rehearsal. I call it 24 in 24. That's 24 topics, all 24 of our gold topics for the course in 24 minutes. And this is a dress rehearsal of the first 18 out of those 24. So you're still working on the D topics as part of your quiz today. But tonight, all 24 are going to be made available, and we'll look at them again in a live stream at about 9 p.m. But for now, let's just take a quick look through the first the first 18 of the 24 important gold topics for the semester. So the first set of topics dealt with algebra and functions. And the first was just what we called exponent gymnastics. How do you simplify an exponential expression completely when that expression has things like radicals and negative exponents and stuff in it? Well, the radicals, remember, turn into fractional exponents. That's a conversion that's especially important later on in calculus. We can use distributive properties of exponents over multiplication. And then the power to product property for exponents, the quotient to difference property for subtracting exponents, and then simplifying, we find out that a negative exponent, such as we have down here at the bottom, can be simplified by trading out multiplication for division, so moving that power into the denominator. And then multiplying exponents is the same thing as adding, and then we're done. Right. So that process of navigating the exponent properties and the order of operations and converting fractional exponents and negative exponents into other forms, that's an important topic as we begin our algebra component for the course. The second topic was about factoring and what factoring has to do with our understanding of polynomial and rational expressions. So if I wanted to subtract these two rational expressions, the first thing I would want to do is factor everything in sight, because then I find out that there's actually a factor these two denominators have in common that can make it easier to find a common denominator, which we need to do whenever we're adding or subtracting rational expressions. And once I've found that common denominator, I can add or subtract just by adding or subtracting across in the numerator. And then when I simplify the algebra up in the numerator, I find out I get something like this, x minus 16 over this product, which if I wanted to, I could multiply that product back out and have my final answer. But where you're likely to screw up in this algebra is you're likely to be too greedy and try to cancel something that doesn't cancel, like reduce this 16 and this 4. But that is not permissible because we can only cancel factors in an expression. We cannot cancel terms which are added or subtracted. So for example, we could have canceled these x plus 4s because they were factors in their respective expressions, but the 16 and the 4 are being subtracted or added, and therefore they are not factors, they are terms, and we can't cancel terms, only factors. How do we deal with linear equations and linear inequalities and point-slope form? So this problem asks us to find the values of x for which the line that passes through these 2 points, P and Q, lies beneath the line with the equation y equals x plus 1. So when is the green line underneath the purple line? Well, to figure this out, we need an equation for the green line. And one of the most important skills is finding an equation for a line that passes through 2 points, for which finding the slope is job number 1. The slope is the difference in the y values divided by the difference in the x values. In this case, that slope is negative 2. Once I know my slope, and I know a single point, I can write a point-slope equation for that line. And once I have an equation for both lines, then finding out when the green is underneath the purple is a matter of figuring out when minus 2x plus 9 is less than or equal to x plus 1. We can solve that inequality by subtracting x from both sides, subtracting 9 from both sides, and then when we divide by negative 3 on both sides, remembering that inequalities reverse when we multiply or divide both sides by a negative number. So I get x is greater than or equal to 8/3, which I can find on my graph as the portion of the x-axis which lies to the right of this intersection point. And in interval notation, 8/3 is the lower endpoint, infinity is the upper endpoint, so to speak, and 8/3 is included, so we use a square bracket. Then we turn to functions. A function is any rule or relationship between quantities in which each input has only one output. And we can come up with ways of depicting functions in a whole lot of different ways. First of all, if I have a verbal description, such as the relation that every person in the US bears to their biological father, is it possible for a single x to have 2 different y's? Can a person have 2 different bio-dads? And that answer is no. Every x has only a single y, and therefore this relation is a function. And the domain of this function is the set of all permissible inputs, which in this example would be the set of all US persons. On this graph of x versus y, I find out that a single x value, such as this x right here, can have two different y's, because this vertical line crosses my graph in more than one spot. And therefore, since a single x can have multiple y's, here y is not a function of x. This graph has failed the vertical line test. In this data chart, I have a bunch of x's and a bunch of y's, and I have a repeated value of x. X equals 2 appears twice. But because when it appears twice, it has the same y value both times, it's not the case that a single x has multiple y's, and so this data table still represents a graph, represents a function. And in this function, the domain is the set of all x values that we see represented right here, which includes -4, 2, 0, and 9. We don't have to list the two separately because the domain is just a set. In this equation that relates x and y, we can test it for whether y is a function of x by solving it for y. And when I solve it for y, we get an expression that is single-valued. There's only a single value of x plus 1 over x for any value of x. And so this is a function. Y is a function of x. And its domain is going to exclude any value that makes that expression undefined. And those expressions are the ones where x is equal to 0. So we take x equals 0 out of the domain, and we don't include it. So the domain here is all x values except for x equals 0. Graphs are the most powerful ways of understanding visually what a function does. I can find the domain of a function from its graph just by squishing the graph onto the x-axis and asking how much of the x-axis does it cover. In this case, it appears to cover the whole thing. The range is a set of all y values, which if I squish my graph onto the y-axis, I find out that this graph only covers that portion of the y-axis from -4 to infinity, inclusive of the number -4. The x-intercepts are the places on a graph where y is equal to 0. I can read those directly off of my graph right here. X equals -2, x equals 0, x equals +2. The y-intercept is the place where x is equal to 0, which I can read off of this graph is the point 0, 0. If I want to know what the value of f of 1 is, I'm asking for the value of y when x is equal to 1. I can find that by going to 1 on the x-axis and reading off the corresponding y value of the point on the graph. In this case, that's -3. The reverse process happens if I want to solve the equation f of x equals -3, so I know the y value and I'm looking for the x value. So I go to y equals -3 and I look to my left and right. And in this case, it turns out there's 4 different x values that all have a y value of -3. And so this equation actually turns out to have 4 solutions. I can find them by the places where the horizontal line y equals -3 intersects my graph. Finally, graph transformations. How do I graph a complex function starting from a basic shape and applying a set of transformations? Here I'm starting with this basic shape that has this equation, and I want to know how to graph this function. So I'm going to apply transformations in sequence. First of all, thinking about all the multiplying or dividing that I might need to do. I'm going to multiply by this -2 out in front, and that's going to vertically flip and also stretch by a factor of 2 my graph. And then I'm going to do my adding and subtracting. If I add 4 to my function, that's going to shift my graph up by 4 units. If I add 5 to the x inside the parentheses, it's going to shift my graph to the left by 5. And remember, when we're acting directly on x, to use reverse psychology. Adding 5 to x does not move my graph to the right, it moves my graph to the left, because it's moving the x-axis to the right. So that's for graph transformations. And that closes our initial study of functions in algebra. So where did we go next in our B topics? Our B topics began by thinking again more carefully about linear functions and slopes and intercepts. So here's an example of a problem where we know the price in dollars per pair at which a certain quantity of sneakers can be sold. And we know it's a linear function, and we begin with 2 known data points. So how do I find a linear function that models that behavior? It's going to have a graph that is a straight line through those 2 points. I can find an equation for it by first again finding the slope, which is the difference in y values divided by the difference in x values. I find that quotient, and that number is -0.2. If I want to use slope-intercept form, I now know that the slope I can use is -0.2. To find the intercept, I just need to take one of my points, say 150, 90, plug it in for my x and y, and then solve that equation for b. I find out b is 120. So what do these slopes and intercepts actually mean? Well, to contextualize the slope, I'm going to add my units back in. This 30 is 30,000 units of shoes sold. This -6 is -$6 decrease in the price each. And so the units of this slope are dollars each per 1,000 sold. So in a sentence, I would say, for every increase of 1,000 pairs sold, the price per unit is going to decrease by $0.2. So add those units back in, it helps us to interpret the slope. Meanwhile, the intercept happens when the value of x is equal to 0. Here x is the number of shoes sold. So when I sell no shoes, I will sell no shoes at all if I charge a price of $120 per pair. Anytime we have a linear model, we can get information into and out of it by either specifying an x and solving for y, or specifying a y and solving for x. For instance, if I want to know at what price 200,000 pairs are going to be sold, I'm saying x is equal to 200 and asking for y, which I can find by evaluating f of 200 and finding out that's equal to 80. Conversely, if I want to know how many pairs are going to be sold if the price was 0, then I'm specifying a value for y and asking what's the value for x. And so that requires me to solve the equation f of x is equal to 0. And that just requires a little bit of algebra to get that x by itself. I find out x is equal to 600. Notice that secretly here we've asked for an intercept, because we've asked for when y is equal to 0, so we've asked for the x-intercept of the graph of this function. So be on the lookout for intercept language. Finally, when you're interpreting these quantities, always mind your units. My x's here were measured in thousands of pairs sold. My y's were measured in dollars per pair. So this y value was $80 per pair. And this x value down here is 600,000 pairs of shoes. Don't forget those units, or your conclusions are going to make no sense to the person you're describing them to. Next, we looked at what happened if our data points don't exactly follow a linear model. We could use technology and a linear regression to nevertheless come up with a line of best fit that best captures the whole trend in the data. So we put our data points into a grapher, Desmos, Excel, a spreadsheet, whatever, and we come out with a regression equation that looks like this. We know a slope, we know an intercept, and we also are given a correlation coefficient or a coefficient of determination, an R value or an R squared value, depending on the software that you use. So what do all these things mean? Well, the correlation coefficient tells me two things. It tells me the direction of the correlation by its sign. In this example, the correlation between your average drive distance as a PGA Tour golfer and your fairway accuracy is negative. So as my drives get longer, my accuracy gets smaller. And the number here determines the strength of the correlation. The closer this number is to plus or minus 1, the better that the data are an exact fit to the linear model. In this case, it's pretty far from an exact model, and you can tell there's not a great linear clustering of these points. We can also, again, interpret the slope and the intercept as ways of capturing the trend in the whole data. This slope, negative 0.218, means that for every additional 1 yard of driving distance correlates to 0.218% lower of fairway accuracy for the golfer that we're looking at in these examples. And we can also use this equation to interpolate or extrapolate. If you give me an x value that we're interested in, I can plug it into the model and find a y value, for example. Next, we turn from linear functions to quadratic functions. If I had this quadratic function, degree 2, I can find how many real zeros it has by evaluating its discriminant, b squared minus 4ac. I evaluate that discriminant. I find out in this example the discriminant is positive. And when the discriminant is positive, I know that I have 2 real zeros for this function. What those zeros are can be found as the x-intercepts, or the solutions of f of x is equal to 0. I can find that either by using the quadratic formula or by factoring, which is a much better idea when we can get away with it. When I factor this expression, its two factors can be broken apart, set equal to 0, to find that the zeros are x equals a quarter and x equals negative 3. What's the y-intercept? The y-intercept is just the value of f of 0. And when I plug 0 in for x, the value of this expression turns out to be negative 3. Now, what about the vertex? Where does this parabola reach its azimuth or its nadir? Where does it turn directions? That's going to happen for a value of x that's equal to minus b over 2a. In this example, that gives me x equals negative 11/8. That vertical line is also the axis of symmetry for my parabola. Then the vertex is going to have x value negative 11/8 and y value equal to f of negative 11/8, which if I plug that in, I get negative 169 over 16. That gives me the coordinates of my vertex. Taken together with my x and y intercepts, I now have a complete picture of what the graph of this parabola looks like. I can then also put on my graph transformations hat to figure out that this is really a transformed version of the basic shape y equals x squared. And it's going to look like x minus 11/8, negative 11/8, the quantity squared, plus negative 169 over 16. There are my horizontal and vertical shifts. They're exactly the coordinates of my vertex. And then my vertical stretch is nothing more than my leading coefficient, my value for a. But if I have a quadratic function, that vertex can answer optimization questions in an applied context, maximum and minimum value questions, which are really important in a lot of situations. If I want to know how to maximize the sales revenue, if the sales revenue follows this quadratic function, then I really just want to find the vertex. Now, how am I going to know that this vertex is a maximum? and not a minimum? Well, it's going to be a maximum because my parabola opens downward. And I know my parabola opens downward because my leading coefficient, my a value, is negative. So when a is negative, the vertex is a maximum. When a is positive, the vertex is a minimum, which is a little bit reverse psychology. All I need now to do is find the vertex. The x value of the vertex, again, can be found in standard form at minus b over 2a, which in this example is going to give me 300. And then the y value is found by plugging minus b over 2a back into my function. Plug 300 into this formula, we get 33,300. That's my y value for my vertex. And my vertex tells me the maximum. And so how we communicate this is we say that if we were to sell 300,000 pairs of these shoes, we would generate a maximum of 33,300. So in other words, $33.3 million of sales revenue. Finally, how do we solve a quadratic inequality? We can do this by using a tool that we end up using a lot more later in the course, which is a sign chart. First, I want to rearrange this inequality so that one side of this inequality is equal to 0. Anytime we're using quadratics, that's a good idea. Then I just want to figure out where is this expression positive and where is this expression negative, because we're interested in where this expression is non-negative. I can find that by factoring the expression, and then I can create a sign chart to show what the sign of each one of these factors is, because we know each one of these factors is equal to 0 at respectively x equals 1 and x equals negative 5, but equals is not good enough for our inequality. We need a sign chart to get a closer look. So in our sign chart, I know that x minus 1 is going to turn 0 when x is equal to 1. But on the left side of x equals 1, this expression is negative, and on the right-hand side of x equals 1, this expression is positive. Similarly for x plus 5, at negative 5, that expression is 0, but to the left it's negative, and to the right it's positive. So when I multiply those two expressions together to give me the expression I care about, I can find the sign of their product. Negative times negative is positive. Negative times positive is negative, and positive times positive is positive. I'm looking in my inequality for where my expression is positive or 0. And so I care about this part of the number line, that part of the number line, as well as the places where the expression itself was 0. So the part I care about is shaded right here, from negative 5 down to negative infinity, and from positive 1 up to positive infinity. So the solution of my inequality is x is less than or equal to negative 5, or greater than or equal to 1. And in interval notation, that takes me from negative infinity to negative 5, and from 1 to infinity. So that closed our book of the study of quadratic functions and inequalities. And from there, we were able to amp up the degree and study polynomials as well as rational functions as well. So how do I understand the salient features of a polynomial functions graph? First of all, if I want to understand what its leading term, in this example negative 3x to the fourth, tells me, it can tell me the end behavior. Where does f of x go as x goes to plus or minus infinity? When my degree is even, my end behaviors are the same. Either both go to positive infinity or both negative infinity. When my degree is odd, the behaviors are opposite. One goes to plus infinity and the other side goes to minus infinity. And which is determined by the sign of the leading coefficient. In this example, my degree is even, it's degree 4, and my leading coefficient is negative. And so I know that as x goes to plus or minus infinity, f of x is going to go to negative infinity in both cases. So the leading term classifies my end behavior. To go any further, we can find the y-intercept without factoring, but to find the x-intercepts, the zeros, we're going to need a factored form. So if we can factor this expression, its factors are going to tell me the x-intercepts, or the zeros, of this polynomial, and the multiplicities of those zeros. So now that I have this factored, each one of those factors, when I split apart, because I have a 0 on the other side of the equation here, is going to correspond to one of my x-intercepts. X is equal to negative 2 is the 0 that I get from this x plus 2 factor. X equals 0 is what this factor of x is telling me, and x equals 1 is the x-intercept that corresponds to the factor x minus 1. So there I see what my zeros are. Their multiplicities are the exponents that we find on these factors in the formula for f of x. Now what do those multiplicities tell me? They tell me the basic shape of the graph at and near those zeros. So multiplicity 2 means that my graph is parabola-shaped. Multiplicity 1 means my graph is line-shaped near those x-intercepts. And so what this is doing is it's roughly, together with the end behavior, it goes down to minus infinity at both ends, giving me a rough shape of the graph of my function. That's super powerful. All we had to know was the end behavior as we go towards the infinities and the local behavior near each one of the zeros. The fundamental theorem of algebra also constrains the relationship between the degree of a polynomial and its number of zeros and its number of turning points. For example, if I want to come up with a graph that does all these things, it has these two x-intercepts, it has this end behavior, it has a y-intercept right there, and it also has 5 turning points. So I'm going to place these 5 max and min points on my graph. Right? So my graph is going to look roughly like this. Can I come up with an equation that does this? Well, the fundamental theorem of algebra tells me that the degree of my polynomial has to be at least as large as the number of real zeros. So my degree has to be greater than or equal to 2 because I have 2 real zeros. But also that the number of turning points is less than or equal to the degree minus 1. So if I have 5 turning points, my degree has to be at least 6. Also, because of what we know about end behaviors, in this example my end behaviors are the same, and so the degree of my polynomial has got to be even. If the end behaviors were opposite, then my degree would have to be odd. Finally, as x goes to positive infinity, its end behavior follows the sign of the leading coefficient. And so in this example, because we end up at negative infinity as x goes to positive infinity, that means that my leading coefficient has to be negative. So I know now that I have a polynomial with a negative leading coefficient whose even degree is at least equal to 6. And also, we know 2 of the x-intercepts, and so we know 2 of the factors. So I'll put those factors in there, x minus 5 and x plus 4, to correspond to these zeros. I want a degree at least equal to 6, and so let me take and make this one multiplicity 5 and this one multiplicity 1, so my degree is equal to 6 at this point. I'll fix my leading coefficient to be negative, and then what negative number I use is exactly the one I would need to make my y-intercept equal to 12. If I plug 0 in for my value of x, this factor ends up being equal to 4, this factor ends up being equal to 3,125, and so I get 12,500 is the value of this thing, and I need it to equal 12. So what I really need is, and this is a typo, let me fix it right now, 12,500 in the denominator, and negative 12 up there in the numerator. So I fixed this leading coefficient just to make the y-intercept that I want. So we have a lot of dials that we can turn to get an equation for a polynomial that does all the things that we want it to do. And there it is. So then finally, how do we understand how the factors and the zeros of a polynomial correspond to one another? Well, the factor theorem tells me that every factor of a polynomial corresponds to one of its zeros. So if I know that x equals 1 is a zero of this polynomial, the factor theorem tells me that x minus 1 is going to be a factor in minus 3x to the 4th minus 9x cubed plus 12x. If I want to find the other zeros, I should therefore find the other factors. How do I find them? By dividing. Right? Because after all, this missing factor is nothing more than the quotient of this polynomial by the binomial x minus 1. To find that, I can use polynomial long division. X minus 1 goes into minus 3x to the 4th minus 9x to the 3rd plus 12x a number of times that I can find by applying this division algorithm. And that quotient is negative 3x to the 3rd minus 12x squared minus 12x, and the remainder that I get is 0, exactly because x minus 1 was a factor, and therefore it goes evenly into this polynomial. So there's my quotient, and there is no remainder. I can continue by factoring this quotient further. It has a greatest common factor of minus 3x that I can bring out. Then it leaves x squared plus 4x plus 4. That's a quadratic trinomial that I can factor as x plus 2 times x plus 2. And now that I've completely factored this polynomial, I see what all 3 of its zeros are: 0, 2, and negative 2. But division can do more than just factor for us. It can also tell us the value of my function via the remainder. The remainder in a division problem is just equal to f of a. So if I want to know, for example, what is f of negative 1 without plugging negative 1 into my function, I can divide my polynomial by x plus 1. Let's do that using the synthetic division algorithm. And at the end of this algorithm, the remainder that we get here is going to equal the value of f of negative 1. Remember, the synthetic division algorithm drops down the coefficient, multiplies by the number in the blank over here, and then adds down the column, and repeats, and repeats. In this example, I do all of that. I get a quotient right here, and I get a remainder negative 18. That tells me the value of f of negative 1. So there are 2 different division algorithms that we can apply, and you can use whichever one is comfortable for you. From here, we moved on to rational functions, which are polynomials divided by polynomials. How do we find, first of all, what is the domain of a rational function? Well, the numerator and the denominator each have zeros, but the numerator's zeros can tell us not the domain, but the potential x-intercepts for our function. So if x cubed minus 8 is equal to 0, that happens at x equals 2, that's possibly an x-intercept. That has nothing to do with the domain of the function, because the domain is controlled by the x values that we exclude when the denominator is equal to 0. So when the denominator is equal to 0, which in this case happens at x equals negative 2 and x equals positive 2, that tells me what the domain of my function is. So I have to exclude plus and minus 2 from my domain, so my domain is the union of these three intervals of the real number line. The fact that we excluded x equals 2 from my domain also therefore means that x equals 2 was not in fact an x-intercept of this function. So this information that we got from the numerator is actually not relevant. Also, you might notice that if you factor this entire thing first, that we get this common factor of x minus 2 in the numerator and denominator that looks like it would cancel. The problem is that if we just cancel it, we're going to miss the fact that x equals 2 still needs to be excluded from my domain. Even if this x minus 2 in the denominator cancels, that factor still needs to be excluded from the domain. It ends up later on, we discover, being a hole in our graph. And that's the kind of analysis that we really ramp up next, is how do we discuss the end behavior and local behavior for rational functions. End behavior has to do with horizontal or slant asymptotes, and those are governed, just as they were for polynomials, by the leading terms. So I look at the leading terms only, I forget about everything else. In this example, the leading terms are minus x squared divided by x squared. I divide that out, I get negative 1. That tells me the y-coordinate of the horizontal asymptote for this function. But what would have happened if I had a higher degree in my denominator than in my numerator? I would have had x's downstairs, and the horizontal asymptote would become 0. In other words, the x-axis. If I had a higher degree in my numerator, then we would have no horizontal asymptote. But if I had a higher degree by exactly 1 more in my numerator, as we did in our last example, x cubed upstairs, x squared downstairs, we would instead have a slant asymptote whose equation we could find from doing the polynomial division of numerator by denominator. Now, it's the factors in the denominator that govern the local behavior, because after all, they govern the domain. Once I know which values of x I need to exclude from my domain, in this example, when I factor the denominator, I find out the values I need to exclude are x equals negative 8 and x equals positive 1. Then I can ask, what is my function doing near those excluded values? For those factors that cancel from both numerator and denominator, we end up getting a removable discontinuity, or a hole. So this has a hole at x equals negative 8. Those denominator factors that do not completely cancel give me vertical asymptotes. In this example, x equals 1 gives me a vertical asymptote. This x equals 2 factor from my numerator tells me that there's an x-intercept at x equals 2. Finally, if I want to know what the local behavior near this vertical asymptote is, I'll set up a sign chart, taking all of my factors and just figuring out what's changing sign at x equals 1, and how. Well, x minus 1 is the only factor changing sign near x equals 1. It's negative on the left, it's positive on the right, and it's 0 at x equals 1. The other factors have a constant sign. X plus 8 is always positive near x equals 1. X minus 2 is always negative near x equals 1. And so f of x is a minus sign attached to an x minus 2 divided by an x minus 1. And so when I take the signs of that x minus 2 and x minus 1, I find out that f of x is negative to the left of this value. It's undefined at x equals 1, and it's positive on the right-hand side. And so this sign chart tells me that x approaches negative 1 from the left, f of x approaches negative infinity, falls through the floor, and as x approaches 1 from the right, f of x goes to positive infinity, it crashes through the ceiling. Finally, we can use everything we know about local behavior and end behavior for rational functions to do the opposite, to take a graph and speculate an equation for a rational function that has all these properties. For example, this graph has an x-intercept at x equals 1, so I know that I want a factor of x minus 1 upstairs in my numerator. It has vertical asymptotes at x equals negative 3 and x equals 0, so I want factors respectively of x plus 3 and x in the denominator. Also, since the local behavior is the same, both crash through the floor here at x equals negative 3, I'm going to want an even power, an even number of x plus 3 factors downstairs. And when the local behavior is opposite, crash through the floor on one side, through the ceiling on the other, I want an odd number of factors. I'll choose a number of 1 factors of x there. If I have a hole at x equals negative 2, it means I need a factor of x plus 2 in both my numerator and my denominator. And then finally, do I have my end behavior right? Well, I have a horizontal asymptote at y equals 0, which means that I need my denominator to have a higher degree than the numerator, which it already does, so that looks fine. But I also notice that f of negative 1 is a negative value. But this function doesn't do that. If I stick a negative 1 in for x, I'm going to get a positive number right now. So to fix that, I'm just going to put a negative leading coefficient, let's say negative 1, out in the front. And this expression gives me a speculative expression that defines a function that has all this local and end behavior that we would want. So that's the first 18 topics in review for our semester, and we did it in about 30 minutes, which tells me that when I produce this for reals later on, I've got to be a little bit quicker in getting through these 18 topics so that I have time for the remaining 6. I will see you again later on tonight at 9 p.m. for a full 24 topics in 24 minutes and a discussion afterward.